Okay, so in this video and the next video, we're going to look at some examples to do with distances between points and lines, or lines and planes, or points and planes, and things like that. So there are some formulas in our textbook in boxes. Generally, if students try to do these problems by memorizing formulas, they get the formulas all jumbled up, and then they're not using the right formula for the right type of problem. And so my suggestion is, rather than memorizing the formulas that are in the boxes, to try to understand the geometry and think through what the formula should be based on that geometry. So I'm going to draw some pictures here, and rather than writing down the formulas that are in the textbook, we're going to try to just use the geometry to understand how we might calculate this. Okay, so we've got a line. That I didn't necessarily draw that line perfectly, but I'm just drawing a kind of a representation of a line, and I've got another point. This is our point and our line that we used in the last video. We already showed that this point is not on that line. So this point is not on the line. We already showed that by showing that it made an inconsistent system. And what I want to find is the distance from that point to that line. And so when I think about measuring that distance from that point to that line, there's a lot of places I could measure that distance to. But what we want to measure is, if we were going to travel from the point to the line, we would pick the closest place on the line. So that would be here, and we would have a right angle there. Okay, so with a right angle and with what we've been working with lately, we might think about a triangle, right triangle, and some vectors along the right triangle, along sides of the right triangle, and we can use some things with projections, dot products, cross products to find sides of that triangle. All right, so I can get a couple of vectors here, and we can draw them in lots of different ways here, but I could get a point, another point over here. I'm going to call that Q. We've got points and lines and planes with all kinds of different names here, but I'm going to just a random point, some other point on the line, and I'm going to call that Q. And I could make a vector from Q to A. And I could make a vector also along the line. It's easy to get the components of a vector along the line. And that vector could have its tail at Q if I want to draw it there, or I could have its tail somewhere else. So just draw some other vector here that's along the line. And we did some things with dot products and cross products where we labeled sides of a right triangle previously using dot products and cross products. So if I think about this angle here, this is the side opposite that angle. Opposite and hypotenuse have to do with the sine. And if you think about the dot product and the cross product, the dot product has to do with cosine. That's related to the adjacent side of your triangle. And the cross product has to do with the sine. So that's related to your opposite side of the triangle. Okay, so let me give this vector along the line a name too. We'll just call that vector V along the line. All right, so if I draw this picture and just think about the geometry here, you should see how you can use dot products or cross products to find the distance you need. This is the opposite side, so this has to do with the cross product. So if I take the cross product AQ cross V and the magnitude of that cross product, AQ cross V, the magnitude of that cross product divided by the magnitude of the adjacent side here. Yeah, that will give me this side of the right triangle. So we did a prior video where we looked at along and across perpendicular, so along and perpendicular with some forces, and we used some things like this to measure how much is along and how much is perpendicular to another displacement vector. So this is the same triangle, just with different labels that we looked at before here. And then this side here would be AQ dot V, magnitude of that divided by the magnitude of V. Right, so this is the same kind of triangle that we looked at before. All right, but for the distance that we're interested in here, we want this. All right, so let's go ahead. We'll find another point on the line. That's easy to find. There are a lot of ways you could do that. You could plug in different t values and get them, but you can also just, if you plug in t equals 0, you get a point on the line. So I'm going to call that Q. So 3, 4, -3. I can get the vector AQ. Oh, actually, the way I drew this here on my picture, I have QA. So I think I started to write it that way and corrected myself. So QA. QA. All right. So QA. So I need the vector from Q to A. All right. So if I start at Q, so x coordinate of 3, and I end up with an x coordinate of 1, my change in x is -2, and then from 4 to 2, my change in y is -2. From -3 to 0, my change in z is 3. All right, so there's QA. Vector v along the line, so the coefficients of the t in that equation of the line gives you the components of a vector along the line. Okay, I need to do a cross product. So QA cross V. We'll set up our little determinant of a matrix here. I, J, K, -2, -2, 3, -1, 2, 3. And if I calculate my cross product here, you should be getting to the point where you're a little more fluent in calculating these cross products. Sometimes it takes a little while, but we'll have -6 minus 6, so -12 in the I component, and then remember the minus in the J component. And so if I eliminate that row and column, I'll have -6 minus -3, so -6 plus 3 will be -3. So there's a minus out here, that'll make that a +3 in the J component. And then in the K component, I'll have -4 minus 2, -4 minus 2, so -6 in the K component. And you can, of course, write that with the brackets and commas. Here I have it in the IJK notation. I might go ahead and tidy this up just a bit so that I don't mess up the signs here. So -12, +3, -6. All right, so now all that's left is to find a couple of magnitudes of vectors and then find this quotient here. All right, so the magnitude of QA cross V, QA cross V. So square root of -12 squared is 144, plus 3 squared is 9, plus -6 squared is 36. So we get the square root of 189. No, that's not right. Let's see. Yeah, maybe. 190, I don't know. I'm going to mess this up. 144 plus 36 is 180 plus 9. 189, that was right. Okay, square root of 189. And then the magnitude of V, I'll just go up here and do this. So magnitude of V, square root of -1 squared is 1, plus 2 squared is 4, plus 3 squared is 9. I can do that one. Square root of 14. Okay, so now we just need to find the distance that we were after to start with. So the magnitude of QA cross V, square root of 189. And the magnitude of V, square root of 14. It's possible to do some simplifying here so that you can simplify with radicals if you want to, but should be equivalent in this form. I'm okay if you leave it in that form. All right, so again, the main idea here is partly to be able to calculate this distance, but really to be able to think about the picture and the opposite and adjacent sides of that right triangle and understanding how to use dot products and cross products to help you find those distances on those two sides of that triangle.